Okay, so just a clarification, when you get that calculation, when the dust settles and you find the inverse and then you multiply them out, you should end up with a 1, 0, 1. So 1 is not a multiple of P, so these two fall in that, but this third entry does not, so this is not an element of NP. So what can we conclude from that? That tells us that the product of this coset A times the second coset B is not the same as B times A. Not abelian, and cannot be cyclic. Okay, we'll return to this shortly, but I'd like to maybe look at some other example in some more detail, maybe even prove a theorem, and then we'll come back to looking at some more, such as how many elements they are, and maybe what are some of the orders of each of the elements. Also, I should point out the value of P being a prime is really, so far, everything would say through for any integer P, right? That, you know, the, 1 is never going to be the multiple of any integer other than 1. So this could really work for any, P doesn't have to be a prime, P just has to be any integer different from 1 or negative 1. Okay, so let's go on and look at a different set. Still look at the Heisenberg group, but let's look at a different factor group. And we'll do that by choosing a different subgroup. So the subgroup we choose here factor group, and again, sometimes they'll use the terminology quotient group, same for factor group. So now we want to take out our same set. Let, again, Z of G be the center. And so I claim what is Z of G it's just going to be all elements of this form. So basically, two of the entries have to be 0, and this third, the first row, second column, second row, third column, but the first row, third column, that can be any integer at all. So I claim that's the center. Let's see why. Before I do that, let's see the note. Z of G is always, in any case, in any group, a normal subgroup. So for any group, G, if we mod by the center, is always a factor group. So again, to show this, we'll show double containing. We'll first show everything in that form has to be in the center, and then we'll show everything in the center has to be in that form. And one of those is a little bit quicker to show than the other. So if I look at if I calculate this times a typical matrix x1, x, y, z, what I end up with is 1 x y plus b 0 1 z 0 0 1, and this is true for any b in B. And the same thing if I did the other calculation. That should end up being 1x y plus b 1 0 z. And this is true basically for any matrix in the group, so that involves taking any three integers x, y, and z to give us our matrix in Z. And for any matrix in this set, which involves let B be arbitrary. And we look at these two things, maybe I even write it this way. I mean, it's actually, if you want to kind of keep it uniform, it would be B plus Y, but that's still going to be, these two things are still the same. So this tells us that this set is contained in the center of the group, because every element in that set commutes with every element in Z. What about the other conclusion? Okay, all those, this set, every element in this set certainly lies in the center, but is there anything else? So how can we look at that? So that's a little bit trickier. Let's suppose we had some element like this in the center. So it can commute with every matrix in the whole entire group. So what I want to do, I want to make a couple clever choices for matrices that commute. And eventually what I really like to see is that, A has to be 0 and B has to be 0 as well. So let's see how we can do that. Right, again, if this matrix is in the center, it's got to commute with everything in G. So let me look at a couple of examples in particular. So in particular, I think if I have look at this calculation, then if this matrix is in the center, these two things have to equal so what do I have then? So I have and I'm not really even interested in all of these entries, so that's why I'm just putting dashes here. But let's look at what goes in this column. So here I would just have B, and then here I would have B plus C. So certainly if that commutes, those two products are going to be equal, so the resultant two matrices will be equal. In particular, these two entries will be equal, so B equals B plus C. So B equals B plus C. So C has to equal 0. So they look like, okay, a matrix, maybe it's something like this form, but it's actually, so the matrix has to become what? If C is equal 0, it would have to be 0, A, B, 0, 0, 0. Right? I've now shown that if this matrix is in the center, this C has to equal 0. And then from there, I can use a similar argument to show that A equals 0. So since that matrix is in the center, in other words, since it commutes with all elements of G, we would have that one A, B, 0, 0, 1, 0, 0, 1. And we'll commute it this time. I think I'm going to use 1, 0, 0, 1, 1, 1, 0, 0, 1. And if this matrix really is in the center, which I'm assuming, and I'm trying to force that both A and C have to equal 0, if I do the product the other way, those two should be equal to 0. So what does that tell us? If we go through, and again, we have a bunch of matrices, but again, let's just focus in on that first row, third column. So there's a lot of this. There's 8 entries I don't care about for this purposes. And then this next one I'd flip here. This would be B. No, over here. This would be A plus B. And then over here, this would just be B. So A plus B equals B, or A would have to equal 0. And so in fact, if we assume a matrix like this is in the center, what I've just proven up above is that A equals 0 and C equals 0. So that's the other containment, that everything in the center is contained in this. And therefore, this set is exactly the center. So both together prove that the center Z is, the center of G is exactly this set. And now we know, of course, as we marked earlier, that the group of cosets will form a group, because in any group, the center is a normal subgroup. So we try to see how many different cosets are there. And so I claim there are infinitely many different cosets. In other words, the order of the factor group G mod the center is infinite. And the way I do that is I'll exhibit infinitely. I won't even give all cosets. once I show there are infinitely many distinct cosets, that's enough to show that the total number of distinct cosets has to be infinitely many. So let m and n be in Z with m not equal to n. Then if one looks at this calculation, 0, 1, m, 0, 0, 0, 1, 0, 0, 1. The inverse of that times the other representative, if we go through this calculation, I get that, and this is not an element of the center. Since this right here, n minus m, is not equal to 0. Right? Remember, in the center, we have to have these two elements be equal to 0. So what does that tell us? So for each n not equal to n, this coset is not the same as this coset. And so we've got infinitely many ones, right? Like if I put a 1 here, I put a 2 here, a 3 here, a 4 here, etc. That would give us right there infinitely many cosets. So there's at the very least, for each integer we get a different coset, and so there's got to be infinitely many cosets. Okay, let's look at whether it's abelian or not. Is it abelian? What do you think? And I say it is abelian. So let's look at a calculation. Let's look at two elements in this fact group. So we have u, v, w in Z, and x, y, and z in Z. When I say Z, I mean the integers. So let's look at this times z of g, and then another coset, let's just use x, y, and z as my letters. And let's look at this. And if I go through, I end up with, and I claim that's equal to 1x, 0. This coset times the other one. And I'm claiming those two cosets are the same. So what does that give us? So then basically we're saying, I shouldn't say these are equal. Are they equal? Is. So really we're asking is say that coset I'd multiply these two representatives together. So I look, is that coset equal to the coset I get by multiplying the two elements in the reverse order? Well, let's look at this product. Again, the details I even left this out. You can maybe use a graphing a TI-89 or some symbolic way to go a shortcut, or you can roll up your sleeves and actually calculate them. But I believe if you do, and so I've got this product here, times this product. Notice that the inverse is outside, so multiply first and then take the inverse. So think of that as being the inverse of this. And then times this. Again, I'm not going to run through step by step of what the product of these four matrices is, so you have to first find a product here, then take the inverse. That gives you a third matrix. Then multiply these two matrices. Make that result, multiply by this. But lo and behold, when the dust settles, you end up with 1, 0, 1, 1, 1, 0, 0, 0, and then here you have a mess. You don't even care what it is. The key is that these two have to be equal. I think if you're keeping score at home, this ends up being U or W plus 2UZ plus XZ plus minus X minus U minus X times W plus Z. You can actually even sum of that, you can see this is a UW that would cancel with these. This would be another negative UZ, cancel with one of those. And this is going to be XZ. And then this cancels with this. So it actually maybe even, well, this I believe may simplify out as just a positive 2UZ and a negative UZ, so it may end up being just UZ when all the dust settles. The point is, it doesn't matter what's up here. This could be any integer. The key is that these two are the entries you really want to look at. They have to be equal to 0. And a calculation will show that. So why is that? Well, with this in mind, this matrix here is an element of the center, right? Because it's got zeros in these two spots. So what we have then is the following. This is in the center of G. So that tells us these two this coset has to equal the one I get when I multiply in the reverse order. So basically the coset group is abelian. And again, this I'm not going to work through the details. It's a lengthy calculation. Again, I encourage you, if you want, you can use a graphing calculator that has symbolic thing or Mathematica, some software to go through. Or again, if you not know, we have a formula for, in this case, what the inverse of the matrix here. It's not too bad, and if you go line through and make the calculations, that's what you'll end up with. So this factor group is abelian, right? Because I've just shown the product, if I multiply one coset determined by A times the coset determined by B, I get the coset determined by AB. If I multiply the coset of B determined by B times the coset determined by A, I get the coset determined by BA. And I've just shown these two cosets are the same because the inverse of this fellow times that is in fact in the center. So we do have it abelian. What about the orders of elements in it? So what we claim, the identity has order 1. The order of each element of G mod G of Z besides the identity has infinite order. So what does that mean? For an element to have infinite order, that means no matter what positive integer you raise it to, you never get the identity. For finite order, that means there's got to be some positive integer that when you raise the element to that positive integer, you do get back the identity. So let us prove this. Why? Suppose n is in Z, n is positive, might as well make n strictly greater than 1. I guess we even make n greater than or equal to 1. With what? The coset determined by some element I guess I gotta scoot over on the board or wide range. Let me zoom out a little bit just to give myself some more. I'm just gonna move over and then erase this. So it's going to work over here, but I'll just copy the line there. So what does that say? That would say my typical element, which I have as this. If I raise this coset to the nth power, I get just the coset, the identity coset. And one thing you remember is any coset, whether normal subgroup or not, the identity coset, the coset determined by the identity, is just the subgroup itself. So what would this mean? This means that, well, again, the way you would raise something to the nth power, a coset, is you just raise the element to the nth power, and that would have to be equal to the identity coset, which would mean what? So if we have something is equal to the identity coset, that means this element, this representative, has to be in the center. Which would mean if we raise this to the n, this would have to be in Z of G. But recall there was a problem way back in homework 1 that this is actually to the n was just 1 NA, and then what was it, NB plus N choose 2 times AC, 0, 1, NC, 0, 0, 1. So that's what would be given by this element. But how could this happen? The only way this could be in the center, remember, to be in the center, these two elements have to equal 0. So NA would have to equal 0, and NB equals 0. But N is greater than or equal to 1, so A would have to equal 0, and B would equal 0. So what does that tell us? The only way you could, the only element to the nth power that's in the center is if both of these are equal to 0. That's the identity coset. So if this element to the nth power is equal to the identity coset, then in fact the element you started with itself must be the coset determined by the identity. So any element that's not the coset determined by the identity has infinite order. Again, the only possible way you can take a coset and raise it to the nth power and get back the identity coset would be if these two elements were 0, which would basically, what's wrong here? Let me correct my mistake in a second, but the only way that could be would be if your initial coset was in fact in the identity coset. Here I guess this should be what? NC equals 0. So C would equal 0. And again, here maybe I've skipped a step as well. Let me throw in a little more details for here. So what you would have is this, the only way this could happen so this can only happen when? When A and C are equal to 0, but this coset, this element here is in the center, so that has to be the same as the identity coset. You can see that because the inverse, these two cosets are equal if and only if the inverse of this times that would be in the center. But the inverse of this is just the identity, so if and only if that product, this element would be in the center. So anyway, we've shown that every element besides the identity has infinite order. But is that cyclic? That doesn't necessarily mean just because you have infinitely many elements and you start raising each element to the power, you get infinitely more elements. Is that still going to give enough elements? And we'll come back in this 1 second. Let me just clarify this last thing and sort of make a general statement. And I think we've noted this before, but what I really make use of there for any group G, some coset AH equals EH if and only if A is in H, where H is a subgroup of G. So I'm not sure, I think I did explicitly state that way back when we were looking at cosets, but that's how I get that this coset, I really don't directly get this coset has to be the identity coset. I actually get this coset here has to be this coset, but this coset itself must be the identity coset because this element is an element of the center. Okay, so let's continue on and let's look at is it cyclic now? Okay, so let us go back to G mod Z of G again, G the Heisenberg group. Is it cyclic? Seems like there's at least a shot. It's abelian, so we can't quickly say there's not cyclic. There's infinitely many elements. If all the elements in the group had finite order, we could definitely say no way it could be cyclic. But here, the elements have infinite order, so it's still got a chance to be cyclic. But it turns out the answer is no. Why? The result of that is a theorem. The reason that results that why check because of the following. So theorem. Let G be any group. If the factor group formed by modding out by the center, G mod the center, is cyclic, then the group itself, G, is abelian. So this is a structure theorem. We actually, by finding out some information about the structure of this factor group, G mod the center, we can get information about the original group itself. Before I prove that, note since the Heisenberg group G is not abelian, it's pretty easy. I think I have some easy examples of some matrices that don't commute. I think that was even the homework. I didn't even ask you to show it's a group. I think I asked you to show it's a non-abelian group. Then the factor group by the quotient of G mod the center cannot be cyclic. Right? Because if it was cyclic, then that theorem would guarantee, if that factor group, the Heisenberg group mod the center, was cyclic, then that theorem would guarantee that the Heisenberg group itself has to be abelian. So let's prove this theorem now. And this proof, it may look pretty scary, but it's actually not too bad. It's a real nice exercise in trying to just use the definition of how we multiply things in the quotient group and what it means to be cyclic and kind of piecing it all together. So let me attempt to prove the theorem. Again, this remark after the note, that's not at all part of the proof of the theorem. That's just going to show how that theorem will allow me to say that the Heisenberg group mod the center is not cyclic. So if the center is cyclic, that means it's got to be generated by some coset determined. What's the coset? Well, whatever that coset, whatever that generator coset is, it's got to have some representative G. So we take any x and y in G. Well, then if G is this cyclic group, So there exists a j integer with x equal to this element to the j, but that's just, or I'd say, so it's got to be in some coset. All right, so let me put in a few more details that are in the notes here. Okay, here we go. X is certainly in the coset containing X. This is one element of our cyclic group. All the cosets are cyclic, so any coset can be gotten by looking at this GZ, this generator coset raised to the J power. And the way we multiply cosets, we multiply the representative. So that's G equal G to the J times Z of J. So there exists a Z in the center with, well, X is an element of this set, G raised to the J times the center. That means it's got to be an element of the center where X itself equals G to the J raised to the G to the J times Z. And I could say a similar element, Y, would be equal to G to the K times Z prime. So, a similar argument shows there exists an integer K and some Z prime in the center with Y equals G to the K times Z prime. Now I'm erasing this here, but what's the conclusion? We want to show G is abelian. So let's do that. So xy would be G, J, Z, G, K, Z prime. Z is in the center, so let's commute it with this. This itself is one element, so we might as well just move this element all the way over here. So this is G to the J, G to the K, Z prime times Z. Right? The center I can commute it past everything. And then these two can commute because it's just the power of G, right? If I have JG's lined up followed by KG's lined up, that's the same as having KG's times JG's. And again, you can put, I think in the notes I put some more details using the properties of exponents. We add exponents. These are integers. Addition of integers is commutative. And then again, the laws of exponents mean this. But this is in the center, so let me slide that over past here. And what did I just, this goes here, so that would, it's GK Z prime G to the J. But lo and behold, this is exactly there it is, Y, and this here is exactly x. Since x and y were any two arbitrary elements of G, we have shown that G is abelian. So with that theorem, that goes back to the example, the Heisenberg group mod the center, that must in fact be an abelian group. That cannot be cyclic because if it was cyclic, by this theorem that I just completed the proof of, the group itself, the Heisenberg group itself would be abelian. And it's not. Now the coset group formed by the center, that does happen to be abelian. That's an abelian group, but that's not cyclic. Okay, so let's move on now. Let's return to the Heisenberg group and that subgroup N sub P. So again, G is still the Heisenberg group, which I think I basically use the X's and Y's or whatever variables you want, 3 integers. And N sub P is also built from 3 integers, but they're not completely arbitrary. Each of these elements is a multiple of P. So A, B, and C are elements of Z. Here, P is a prime. Okay, suppose we had two cosets that were the same. And I'll use X, Y, and Z, and I'll use U, V, and W as before. What does that tell us? That tells us that, as we saw, what's the fundamental relation between cosets? The inverse of one representative times the other representative. If that's in P, then the inverse of one representative times the other representative has to be in the subgroup you mod by. If that product is in N of P, then the coset determined by this element would equal the coset determined by the other element. So we calculate this. This gives us what? 1 U minus Z, U minus X, 0, 0, 0, 1, 1, W minus Z, and then V minus WX minus YZ plus XZ. Okay, let's take a step back. What the heck did it mean to be an NP? Well, you need all 3 of these entries have to be divisible by P. So P would have to divide U minus X, if this is in the center. And P would also have to divide W minus Z. And there, okay, all P would have to divide this whole big product. Which, if I rearrange, this is really v minus y, and then minus x times w minus z. And so if P divides this whole difference, if P divides w minus z, we can conclude that P would have to divide z minus y. V minus y. Right? P divides this difference here and if P is going to divide this whole difference and divides this term, it's also got to divide that term. Perhaps maybe I should prove that or show that as detail, but again, we're really saying if P divides A and P divides B minus A, then P must in fact divide B. So I think if you go to divisibility relationships, you can see why that's got to be the case, right? You could add these two together, you would get B minus A plus A is just B. But A is something times P, B minus A is something else times P, so if you add them together, you'll end up with something times P. So B has to equal something times P. Okay, so what does that tell us? That basically tells us that the only way two things could be a coset is if this difference is divisible by P, this difference is divisible by P, and this difference is divisible by P. So each choice of 0, 1, 2, ... up to P minus 1, for each distinct choice for X, Y, or Z gives a distinct coset. And again, in terms of basic probability, you'd think sort of this is an independent. In other words, whatever number in the set I pick for, say, X, each of those choices, my choice of which number I pick for Y is independent. So that's really, you can think about this, you have P choices for X, each of which has P choices for Y, each of which has P choices for Z. So there are P cubed different choices. So how many different cosets do we have? Well, that actually, I think that tells us maybe what I've shown is that it's at least P cubed. We have at least this many. But how can we show we have at most that many? Well, if R1, R2, and R3 are the remainders after I divide x, y, and z by p, we would have that this coset would have to equal that coset. Are the, oh, I forgot to, I said it there, are the remainders. But there are, at most, p possible remainders. Namely 0 up to p minus 1. So that means there can be no more than p cubed cosets, right? We have at most p choices for this remainder, each of which has at most p choices for this remainder, each of which has at most p choices for that remainder, so they can be at most p cubed. Thus, we've now got the number of distinct cosets. The order of the factor group is p cubed. Okay, so let's maybe conclude this extended look at the group. We're going to now look at what are some of the individual orders of the elements. So let's look at the possible element order. Possible orders of each element in this factor group. Well, by Lagrange, you have to divide p. I'm sorry, divide p. By Lagrange, it must divide the order of the group, which in this case is p cubed. So here's where the prime really comes into play. And so the only possible orders, again, why is that? You might say, wait a second, Blau, something's up here. Lagrange was about cyclic, about subgroups, not element orders. But remember, the element of an order in a group is the same as the element of the cyclic subgroup generated by that element. Since the element of a cyclic subgroup generated by an element, or any subgroup, must divide the order of the group, the order of the element must also divide the group. Must be, oh, this is terrible. Must, not must be. Lagrange doesn't say what it equal to. It must divide p cubed. So the possible orders are 1, p, p squared, and p cubed. Here's where the prime comes into play, right? If you don't have a prime number, there may be many more divisors beside that, right? Think of something that's not prime. 4 cubed. That's too hard. What is 4 cubed? 4 cubed is 64. But certainly the only divisors of 64 are not 1, 4, 16, and 64. But again, that's because 64 is 4 cubed, 4 is not a prime. If it's a prime number, though, if p is a prime, the only possible divisors of p cubed are 1p, p squared, and p cubed. This we rule out, because remember, way back earlier we showed this is not abelian. So, is not cyclic. So there cannot be an element whose order is the whole group. Right? If there was an element of p cubed, of order p cubed, the whole group itself only contained p cubed elements, so that element would generate the entire group. Okay, so let's look at this. We actually need to split up the case here in a slight argument versus the only odd prime, and here's a bad joke, is 2, right? Odd not in the sense of even and odd, but odd in the sense of different. 2 is the only prime that is even, which you could say makes it the odd prime. And odd as being different from the rest. So I'd like to investigate the individual order. This is still true for when this p is equal to 2. What I've said here is still the case. There's still 2 cubed. There'll still be 8 elements. And the orders still can only be 1, p, and p prime. And unlike a general proof with A's and B's and arbitrary elements that I'll have to do for orders greater than p, p cubed, if the prime p is 2, p cubed is 8. So I really have to look at 8 cosets. So let's list all the elements. So we've got the coset determined by the identity. And then something else. Remember, the way to get a different coset is to assure all the possibilities to have remainders less than between 0 and 1, which is 1 less than 2 here. So I think I looked at, this is another coset, another element of the group. Here's a third element of the group. Here's a fourth element of the group. How about a fifth element of the group? I got both of these right. This. Oh, that looks familiar. That's my fourth element of the group. My fifth element of the group would be that. Sixth element of the group would be seventh element of the group. And finally, the eighth element of the group. So these are the distinct elements of geometry. Notice, basically, for each of these three entries, I have two choices. Either put a 0 or put a 1. So 2 choices times 2 choices times 2 choices, there are 8 different choices. And let me just check my notes and check what I've written on the board just to make sure none of these are repeated. It looks like I see a repeat. My notes are okay, but what I've written on the board is not. So these two were the same, now they're not. Okay, so let's begin looking at them. So first of all, let's take the easiest one. So remember, you can also put the absolute value sign around this. So this is the identity coset. This has order 1. Again, this is just saving me some board space and time, so I'm not writing the order of this equals 1. What about this element? We look at the next element, look at this. And let me square it. And I claim this is just the identity coset. So let me provide a little bit of details here. Maybe skip a step or two from what I put in the notes. So if I square it, the way you square coset, I just square this matrix. I would get 1, 2, 0, 0, 0, 1, 0, 0, 0, 1, and 2. But this is the identity coset because all three of these elements are divisible by 2, right? Remember what the N2 is. N2 is just the set of all elements where you have these 3 matrix entries have to be divisible by 2. So the order of that coset is going to be 2. Some more of the cosets will have order 2. Will all of them? Well, let's find out. I guess we've got 6 more calculations left to go. So let me pick another one. I think I picked the next one I looked at is 0, 1, 1, 1, 1, 0, 0, 0, 1, and 2. And if I square this, I would just square this representative. This ends up being 1, 0, 2, 0, 1, 0, 0, 0, 1, and 2. But again, these 3 elements are all divisible by 2, so that in fact is the identity coset. So what did I have? So this element here has order 2. Okay, I'm going to erase some of this, but I'd still like to keep the matrices up. Maybe I should erase some of the other matrix. So let me keep running tally. So let me get rid of this. That's the identity, so it has order 1. This one has order 2, so I'll erase that. I've checked this one. This one also has order 2. And now this goes back. I have 1, 2, I have 6 more to check. So let me check this one. I'll move over here. If I look at, well, what's the next one I checked in my notes? Yeah, it was that one. 1, 1, 1, 0, 1, 1, 0, 0, 1. If I take that coset and I square it, I'm really just going to square this representative matrix, so I would get 1, 0, 0, 0, 1, 2, 0, 0, 0, and 2. And again, since 2 is divisible by 2, and 0 and 0 are divisible by 2, this gives us the identity coset so the order of this coset is also 2. And so now I'll erase it because I've eliminated that. I've now gotten 4 matrices, right? The identity and so forth, 3 matrices have order 2. Maybe I'm beginning to think that all matrices have order 2. So let me leave these 4 matrices up for the time being. And let me check the other ones to see if they have order 2. Or should we just stop? So far it looks like we've done three. Besides the non-identity, the other 3 matrices we've tried have order 2. Maybe every element besides the identity has order 2. But, again, that might be a conjecture. We really need to come up with a proof for it, or let's just roll up our sleeves and verify to see if that really is the case. So now we're moving on with this matrix. I shouldn't say that. I should say we're moving on with the coset determined by that matrix. And if I square it, I would square this element, so I would get 1, 0, 2, 0, 1, 2, 0, 0, 1, and 2, which again is equal to the identity coset because, well, this representative is an element of N2, right? Well, this is divisible by 2, this is divisible by 2, this is divisible by 2. So now I can erase this matrix and just say that the order of that coset of the factor group is also 2. So far I've checked 4 elements that are not the identity. All 4 of them have order 2. But let's continue on. Let's look at these 3. So let me look at this. Let me square it. So then they should say what happened so far every time I squared it and I've gotten the identity, and so that means the order has to be 2, unless the matrix itself is the identity, unless the coset is the identity, but I picked the other 7 cosets to be different from the coset determined by the identity. So let me see what happens here. I'll square this, so I will get a 1, and I get a 2. Do I? Let's see. I'll get a 1. I should get a 2 here. And a 2 here. And that. So I would get that as my answer. And that again is divisible by, both of these are divisible by 2, so that is the identity element of our factor group. And so I can conclude that the order of this element is also 2. And let me now erase it, and we're coming down the home stretch, right? Just 2 more to check. So far I've checked 6, there's 7 elements in the group. Sorry, there are 8 elements in the group, 7 aren't the identity. I've checked 5 of them, all 5 of them have order 2. Let me check this now. So if I square this, I would just square the matrices, so that's going to be 1, 2, 1, 0, 1, 2, 0, 0, 1, and a P. And that's not equal to the identity coset. Why? Because 1 is not divisible by 2. Remember, to qualify as membership in NP, you need all 3 of these entries to be divisible by 2. Certainly 0 is always divisible by 2, but 1 is not. So what does that tell us? That tells us that what is the order of this element of our factor group? It's got to be bigger than 2, right? Remember, one way of looking at the order is the small, if it's a finite number, which in this case we have a finite group, it's the smallest positive integer that takes you to the identity. Well here, whatever that smallest positive integer is, it's got to be greater than 2. As I said before, it can't be 8, but it's got to divide 8, so it must be by Lagrange, so it must be 4. Again, going into it in general, for anything, the possible orders for the non-identity, only the identity can have order 1, right? Because A to the first is just A. So if A to the first is the identity, that means A is the identity. So any non-identity element has to have order bigger than 1. In general, the order has to divide P cubed, so it could be P squared, or P cubed. But the group is not cyclic, so it can't equal P cubed. So it can only be P or P squared. Well, when P equals 2, we've shown this element isn't P, so it's got to be, it can't be P to the cubed, it's got to be P squared. And certainly if you took your time, you could multiply this coset by this one more time to find out what the cube is. Take that result multiplied by this coset one more time to find out what the square is, and you would in fact see that you ended up with the identity at that point. But I'm not going to make that calculation. I'm going to use Lagrange to simplify my calculation. Again, what I'm saying here is the possible element orders for the non-identity are either 2 or 4. And so if it ain't 2, it's got to be 4. So it's not true that every element besides the identity has order 2. At least one element has order 4. Then there's a question of what about the last remaining element? Or, which would be this. So let's see what happens here. So let's look at our last remaining element. and let me square it. And as before, I square that here. That would just give me 1, 2, I think I should get a 3, right? 3, 0, 1, 2, 0, 0, 1, 2, which again is not the identity element, because while these two elements are divisible by 2, 3 is not divisible by 2. So again, just like before, the order has to be strictly bigger than 2, but the only possibility is based on the fact the group isn't cyclic for element orders could be 2 or 4. So if it's not 2, the only thing left is 4. So the order of that element is 4. So that wraps up the case when P is equal to 2. We've shown that 6 of the elements, specifically we've indicated which one, one element has order 1, the identity. 5 of the elements have order 2, and then those last 2 elements we showed have order 4. Okay, well, what happens with the final coset? Let's look at what happens when we have order P. So if there's a prime not equal to 2, if P is a prime that's not equal to 2, we claim every element of the Heisenberg group mod that NP, of course, besides the identity, has order equal to P. So let's look at 1A, B, C, 0, 1, 0, 0, 1. And P, and raise it to the P power. So we raise this to our power, again, by that homework 1 problem that I've used earlier today. This is P, PB plus P choose B, AC, PC, 0, 0, 1, 0, and P. Well, certainly this is divisible by P, this is divisible by P. What do we have here? PB plus P choose B times AC. Sorry, P choose 2 is just equal to P B plus P times P minus 1 over 2 times AC. So I pull out P, B plus P minus 1 over 2. And note, P minus 1 over 2 is an integer, since if p is a prime not equal to 2, p is odd. So p minus 1 is even, so p minus 1 over 2 is even. Remember, when you use factoring to show divisibility, you'd have to show that something equals p times an integer. So normally you say, wait, how is this an integer? But this has to be an integer where if p is not equal to 2. That's why we need this separate case. So what does that tell us? This tells us basically p divides, or even here, look at this. We can just say this is equal to the identity coset. Because clearly, this is divisible by p. And this entry right here, I've just shown because p is odd, and p minus 1 is even, is also divisible by p, because it's an integer times p. So again, that just means, how do we know p is the smallest positive integer? Remember, the only possibilities were 1 for the order was 1, which isn't going to be the case if it's not the identity, or if it is the identity, it would be 1, the identity coset. If p is if this is not the identity coset, then p would be the answer, would be the smallest power. So all elements of this factor group, besides the identity, which always has order 1, have order p. And so I think briefly I maybe once mentioned the exponent of a group. So the exponent of this factor group is p, because any element in the group raised to the p power takes you back to the identity. Again, remember, when I say the identity here, I mean the identity coset. So for instance, the order of 1, p, 0, 0, 0. The order of this would be equal to 1 because this coset is the identity coset, right? It may not look like it, but remember, this element, to be in the identity coset, it doesn't mean necessarily that your representative is the identity. What it means is your representative element comes from the subgroup you're modding out by, in this case, NP. So we'll pick up our lecture on homomorphism soon. This will conclude a factor group. Again, a little bit detailed, not really any fundamental theorems in this lecture, apart from that one about the G mod the center. If that's cyclic, then G is abelian. But nonetheless, I hope there was some concrete examples of working through some analyzation of how to analyze a factor group. So we'll end here.